Okay, let's dive in. When we talk about infinity, most of us picture something just endlessly vast. You know, the stars in the sky, grains of sand.
A really, really big number that just keeps going.
Exactly. But today, we're going way beyond that. We're actually on a mission to compare infinities, to weigh them against each other. And in doing that, we're going to expose this really profound, almost devastating truth about computation itself.
That framing is perfect because our goal is to use some real mathematical precision, these tools from George Cantor, to prove something pretty shocking.
It is.
That the set of all possible questions you could ever ask, all the problems in the universe, is infinitely larger than the set of all possible answers we could ever write.
And by answers, you mean computer programs, algorithms?
Exactly.
Yeah.
All possible code. And it's not just a little bit larger. It's a measurably, fundamentally bigger kind of infinity. We're not just exploring a boundary. We're proving the boundary is, for all intents and purposes, completely insurmountable.
Wow. So if the space of all problems is this infinite ocean, then all the code we could ever possibly write is just, what, a handful of islands floating in it.
That's a great way to put it. A countable handful of islands in an uncountable ocean. And to prove that disparity, we have to get our heads around this idea that not all infinities are created equal.
They come in different sizes.
They do. And the size is defined by one core question.
Mm-hmm.
Can you list it?
Okay, let's start there. What does it mean to list an infinite set?
It's what we call countability. When we ask if an infinite set is countable, we're really just asking if we can put every single element of that set into a definitive ordered list, first, second, third, and so on, forever.
Like the counting numbers themselves, 1, 2, 3, 4.
That's a ruler, right?
That's our golden ruler of natural numbers. If we can pair up every single item in our set with a unique counting number, 1 to 1, without missing a single thing, then that set is countable. So if I can give every item a finite address on an infinite list, it's countable, even if the list goes on forever.
Precisely. Formally, that means there's a function from the natural numbers that is surjective. It hits every element in our set. And conversely, you can map the set injectively into the natural numbers. Every element gets its own unique number.
And if a set just resists this, if you try to make a list and you realize no matter how clever you are, you've missed an infinite number of things.
That's when you've hit the bigger infinity. That's an uncountable set. A quantity so vast, so dense, that the very idea of a first, second, third structure just collapses. It breaks any list you try to make.
Okay, our intuition is probably screaming right now that all infinities have to be the same size, so we need some aha moments. Let's start with a classic, the integers.
Right. The set math BVZ. So that's all the positive numbers, all the negative numbers, and 0.
And immediately there's a problem. It feels like it should be twice as big as the counting numbers.
It does. And if you try to count them in the most obvious way, 1, 2, 3, 4, heading off towards positive infinity.
You'll never get back to 0 to start on the negative ones. You'll never count -1, -2. They're just missed forever.
You've missed an entire infinity's worth of numbers. But the genius of the countable argument is that you don't have to count in a straight line.
You can be clever about it. You can interleave them.
You can jump back and forth. You create a pattern that guarantees every single integer, positive or negative, will eventually show up on your list.
How does that work?
You start at 0. That's position 1. Then you take the first positive number.
Well,
That's position 2.
okay.
Then the first negative, -1, position 3. Now the second positive, 2, position 4.
Ah, I see. Then -2, then 3, then -3.
And so on. 4 minus 4, 5 minus 5. Forever. By doing this little dance, you can guarantee that for any integer I pick, let's say -42 million, you can tell me its exact finite position on that list.
It'll be way, way down the list, but it's there. It has an address.
It has a specific finite address. And this proves something fundamental. An infinite set that seems twice as large as the natural numbers is actually the same size of infinity. It has the same cardinality.
That is genuinely surprising. Adding an entire infinity of negative numbers doesn't actually make the set bigger in this sense.
It doesn't. That's philosophical surprise number 1. But number 2 is where it gets really wild.
This is where we go into 2 dimensions.
Yes. The set of all pairs of natural numbers.
Yeah.
Math BBN times math BBN. We're not talking about a line anymore. We're talking about an infinite two-dimensional grid of coordinates.
So listener, picture an infinite chalkboard. In the bottomless corner, you have the point, 0, 0. Then you have 0, 1, 0, 2 going up forever, and 1, 0 going across forever.
And every point in between. Well, 1, 50, 42, a million, a billion, the entire infinite plane. Geometrically, this just feels so much bigger than a single line of numbers.
And again, if you try to count it the obvious way, say row by row, you're doomed.
You are. If you start counting 0, 0, then 0, 1, 0, 2, 0, 3, you will never finish that first row. The entire rest of the infinite grid is left completely untouched.
So you need another clever trick, a way to flatten this 2D plane onto a 1D list.
We need a systematic way to hit every single point, and this is where Cantor's pairing function comes in. It's often called the diagonal sweep or the snake line method.
Okay, the snake line. How does that bring order to this chaos?
Instead of counting by rows or columns, we organize the pairs by the sum of their coordinates. This creates these neat little diagonal lines that are all finite in length.
Walk me through it.
Okay. We start with pairs where the sum of the coordinates is 0. There's only one. 0, 0. That's position 1 on our list.
Got it.
Next, we take all the pairs with the coordinate sum to 1. That's 1, 0, 0. Those are positions 2 and 3.
Right, like a little diagonal slice.
Exactly. Next slice, pairs that sum to 2. That's 2, 0, 0, 1, 2, 2. Positions 4, 5, and 6. Then you do the pairs that sum to 3. 3, 0, 2, 1, and only 3.
I see the pattern. You're taking these finite diagonal chunks and stringing them together, one after the other. You're systematically chewing through the entire infinite grid.
And the crucial part is any pair you can possibly think of, no matter how huge, say 5,000, 7,000, has a finite sum. In that case, 12,000. So you know that eventually our snake line process will get to the diagonal for the sum of 12,000, and that point will be captured.
It will be assigned a specific finite position number on our master list.
You're indeed.
That is a staggering realization. So not only is infinity plus infinity the same size, but infinity times infinity, this infinite plane, is also the same size.
The countable list is an incredibly robust concept. It's the defining feature of this smaller class of infinity. It might take forever, but you can organize all the elements into one single comprehensive list.
Okay. That foundation of countability is absolutely essential. So now let's make the jump. From abstract math to the world of computers and code. Section 3, the size of solutions. If we can flatten a 2D infinity, what about all the software ever written?
We apply the exact same logic. A computer program, when you boil it down, is nothing more than a structured sequence of characters. It's a word from a finite alphabet.
What do you mean by alphabet?
Your alphabet, which we call sigma,
Yeah.
sigma is just all the possible characters you can use. Letters, numbers, spaces, punctuation, symbols like curly brackets or semicolons. The crucial part is that this set of characters is finite.
Okay, but hold on. You're saying we can put all software on a list, everything from a tiny Hello World script to the source code for Windows or, I don't know, a massive AI model. That feels conceptually impossible. The variety, the length, it seems infinite.
It seems that way, but because the alphabet of characters is finite, the set of all possible words you can make from it, which we call sigma, is countable. Theorem 1.16 confirms this. And the proof uses a clever encoding process, a sort of precursor to what's known as Gödelization.
So how do we build this list of all programs?
Well, we don't have to worry about infinitely long programs because any program a computer actually runs is a finite string of code, even if it's millions of lines long. So imagine your alphabet has, say, all our different symbols. We can just assign a unique number to each symbol. So A is 1, B is 2, a space is 3, and so on.
Like a secret decoder ring.
Exactly.
Yeah.
And your whole program then becomes one single, unique, gigantic number in a base dollar number system. Every different program translates into a different natural number.
So every piece of code, every book ever written, every text message, every single tweet, each one corresponds to a unique, specific natural number.
It does. This gives us an injective mapping from the set of all possible texts into the set of natural numbers. And since we already know the natural numbers are the definition of countable,
And a subset of a countable set must also be countable.
it means the set of all possible computer programs is countable. It's vast, yes, it's infinite. But it absolutely fits on a single comprehensive infinite list. We can call them T-dollars, P1, P2, and so on. This list represents our island of solutions.
Okay. The island is built. Now it's time to pivot to the ocean. Section 4, the weight of problems. If all our solutions are on a nice, neat list, where do these uncountable problems come from? We need to find an infinity that actually breaks the list.
We do. And for that, we need to introduce Cantor's most powerful conceptual tool, the diagonalization argument. This is where you really need to buckle up, because this argument, which is surprisingly simple in its structure, is what shattered classical mathematics in the 19th century and then went on to define the limits of computation in the 20th.
So we're looking for a set so large, so dense, that no list, no matter how cleverly we design it, can possibly capture all of its elements.
And that set exists. Theorem 1.17 shows that the set of all functions from the natural numbers to the natural numbers is uncountable. But we can prove it with an even simpler case.
Simpler is good.
Let's just look at the set of all functions that map the natural numbers to only two possible outputs, 0 or 1.
The ultimate yes-no decision problems.
Exactly. Every single infinite sequence of zeros and ones represents a unique decision problem. Does the first number have this property? Yes, no. Does the second? Yes, no. And so on. If we can prove that this simple set is uncountable, then the set of all complex problems is definitely uncountable.
Okay.
So how do we do it?
We use a classic technique, proof by contradiction. We start by making a deliberately false assumption, what I call the fatal assumption.
And that assumption is?
Assume, just for the sake of argument, that this set of all simple yes-no functions is countable.
Okay. If that were true, it would mean we could put them all on a perfect list. Few dollars, F1, F22, and so on, forever. No function left behind.
Yes. And now we visualize this. Imagine an enormous infinite table or matrix.
Let's really picture this, listener. It's infinite in two directions. Down the side, you have the rows, which are all the functions we claim we've successfully listed.
Yeah.
Phi dollars, F1, F2, and 2.
And across the top, you have the columns, which are the inputs we're feeding into them. 0, 1, 2, 3. And every cell in that table, say the cell at row or a lol, contains the result of function feat vol when you give it the input jeller.
And since these are yes-no problems, every single cell in this infinite grid contains either a 0 or a 1. Now, if our list is truly complete, then every single possible infinite sequence of zeros and ones must appear somewhere as one of these rows.
But Cantor shows us how to build a brand new function, a sort of monster function, let's call it loller, that is explicitly designed to be impossible to find on that list.
He does. And the way we define dollars is by focusing only on the main diagonal of this infinite matrix.
The diagonal.
Yeah, that's the sequence of results you get when you look at F1 hours, then F2, then 501 days, and so on. The cells where the function's index number matches the input number.
Okay, so we're just looking at this one specific diagonal line of zeros and ones running through the table. What does our monster function do with it?
Vandals is defined to do the exact opposite of whatever result it sees on that diagonal at that specific spot. We're defining dollars by this flipped diagonal rule.
So for any input, let's say $none, we look at the noth function on our list and our dollars and see what it does with the input one.
Right. And if physicist gives you is 0, then our new function at our gives is defined to give a 1.
And if physenzels gives a 1, then R gives a 0. It just flips the bit.
It just flips the bit. Now,
Yeah.
Here's the critical step. This new function, RR, is a perfectly valid function from the natural numbers to 0. It's made of the same stuff as all the other functions on our list.
So if our original list was really complete, R has to be on it somewhere.
It must be. There has to be some row, some index dr, where our monster function dollar is the same as the function 5gr.
And this is where the logical trap snaps shut.
It is. Because if a dollars is truly equal to 5gr, they have to give the same output for every single input. But let's look at one specific input, the input jr itself.
Oh.
By the very way we defined our monster function dollars, we ensure that gr is the opposite of 5gr.
So they can't be the same function because at that one specific point, the input JR, they're guaranteed to give different answers.
We have a contradiction. We've shown that the dollars is a valid member of the set we were trying to list, but we've also constructed it in a way that guarantees it's different from every single member of that list.
It can't be $50 because they differ at input 0. It can't be $50 because they differ at input 1. It can't be $50 because they differ at input 100.
The contradiction is inescapable. The only thing that can be wrong is our initial assumption. The assumption that the set was countable was false.
The set of all possible yes-no problems is uncountable. It's a higher order of infinity. This is the ocean of problems.
And that is the monumental implication, formalized in Theorem 1.19. The set of all problems, all functions, is an uncountable ocean. The set of all solutions, all programs, is a countable island.
So what does that really mean for us, for you listening? What is the weight of this?
It means that the vast, overwhelming majority of logical and mathematical questions are fundamentally non-computable. Not just hard, not just waiting for a faster computer, but impossible to solve with any algorithm.
This isn't an engineering problem. It's a logical chasm.
It's a chasm carved into the bedrock of mathematics. For every single program we could ever invent, there are infinitely many problems that program can't solve. The majority of what's logically out there is computationally inaccessible to us. That is the weight of infinite unsolvability.
That is a heavy thought. But okay, that's an existence proof. We've proven the ocean exists. But we haven't actually found a monster yet. We haven't named a specific concrete problem that a computer cannot solve.
To get there, we need to sharpen our tools just a little bit more. We need to move from just theoretical listability to algorithmic listability.
This brings us to the difference between just being countable and being recursively enumerable.
Right. In computer science, it's not enough to know a list exists in some abstract mathematical heaven. We need to know if we can write a program that actually generates the list, that spits out the elements one by one.
So countable just means the list exists. Recursively enumerable means I have the instruction manual, the code, to build this list myself.
Perfect analogy. And this distinction becomes pretty brutal when you look at subsets. While any subset of a countable set is, itself, countable, Theorem 1.22 shows us there are subsets of words or languages that are not recursively enumerable.
Why not?
Because the decision of whether or not to include an element in the list might be so complex that no algorithm can reliably make that choice. The complexity of the decision breaks the algorithmic listing process.
Got it. But what about our programs, our solution space?
That's where we get some good news. Theorem 1.23 tells us that the set of all computable functions, all programs, is itself recursively enumerable. We can build that list with an algorithm.
And how do we do that? This goes back to the Gödel numbering, right? Making our list $P, P1, P2, something we can actually construct.
Exactly. We use that encoding process we talked about. Every number, $1, can be translated into a unique string of characters. So we can build a program generator.
And this generator takes a number, dollars, and tries to read it as code.
It does. It translates N dollars into a potential program. Then it runs a simple computable check. Is this string of characters syntactically valid code in our language? Say, MiniPy.
What if it's just gibberish?
Well, checking syntax is a solvable problem. If the string is valid code, we say, great, this is program Pi-Ray. If it's garbage, we just assign a default standard program to that number.
Like what?
The simplest one would be a program that just enters an infinite loop and does nothing forever, like while true counts.
So by doing that, we guarantee two things. One, every valid program definitely appears on our list somewhere. And two, we have a concrete algorithmic way to generate this infinite list, one program at a time.
We do. Every program gets a Gödel number, and we have our constructive, exhaustive, algorithmically generated list of all possible solutions. This list is the foundation for our logical bomb.
Okay, we've built the list of all possible weapons. Now we're going to use the diagonalization argument a second time, but this time, to build one specific concrete function that breaks that entire list, we are finally naming the monster.
We are. We're going to define the self-application function, which we can call phi-test-self-app, with the explicit intent of creating an unavoidable self-referential paradox.
Okay, so this function, what does it take as its input?
It takes the code of any program, $3, as its input.
That seems normal enough. Compilers do that. Debuggers do that.
But this function does something very, very specific. It simulates what program Buller does when you feed it its own source code as its input. It runs pot on all dollars.
The act of self-reference.
The crucial act of self-reference. And then our function, after self-app, is defined to do the exact opposite of what it observes.
The deliberate contradiction. Lay out the rules for me again.
Rule 1. If the program we're analyzing, Beetle-Waller, when run on its own code, eventually halts, then our function, bat-self-app, is defined to go into an infinite loop. It must not halt.
And rule 2.
Rule 2. If the program run on its own code does not halt, if it loops forever, then our function, myTest, must halt and return a value, say, the number 1.
So this is a meta-program designed to look at any program's self-referential behavior and then guarantee its own behavior is the polar opposite.
Precisely. And now we take our beautiful, complete algorithmic list of all programs, P's P1, P2, IL-dots, and we apply the diagonal sweep one last time to prove that this function cannot possibly be on that list.
We're doing another proof by contradiction. Let's imagine that table again. But this time, the cells tell us about termination. Does program PyPL on input $$ halt, or does it loop forever?
And we construct our function, phi-pay-self-after, by looking down that diagonal again, the self-application inputs, PSM-AN, and flipping the termination status.
And we start with the fatal assumption. Assume that this function, beta-tail, is computable.
If it's computable, it must be on our list. There must be some program at some index diggle-dollar, let's call it PJ-dollar, that is the code for via-self-app. They're the same thing.
And now comes the question that breaks everything.
The fatal self-referential question. What happens when we run our program, pjjol, on its own Gödel number, $? What is the result of pjjol?
It has to do one of two things. It either halts or it loops.
Let's check both cases. Case 1.
Yeah.
Assume pjj halts. Well, if it halts, then by the very definition of the self-application function, which pjdel is supposed to be, it must do the opposite of its input's behavior. Since its input, pj halted, then pjj must loop forever.
But PJJ is PJJ1, so that means PJJ must loop forever.
So if we assume pjj halts, we have proven it must loop. That's a flat contradiction.
It cannot logically halt. Okay, so what about the other option?
Case 2. Assume pj$ forever. Well, if it loops, then by the definition of our function, pjjeller must do the opposite. It must halt and return 1.
But again, since PJJ is the same thing as PJJ, that means PJJ just halts.
So if we assume pjjellers, we have just proven it must halt. Another direct contradiction.
So it can't halt and it can't loop, but it has to do one of them. The whole system is broken.
The logic is completely broken. The only way out of the paradox is to admit that our initial assumption was wrong. No such program, pjjellers, can exist.
We found it, our concrete monster. The self-application function is mathematically, logically impossible to compute.
It's a computational black hole. And this function is the direct precursor to proving the famous halting problem is unsolvable. We've just proven you can't write a universal algorithm that can reliably look at any arbitrary program and predict whether it will halt when running on itself.
A system designed to predict the behavior of others cannot even predict its own behavior when it's forced to look in the mirror.
That's the core of it. The first diagonalization proof was abstract. It showed us the ocean of uncomputable problems exists. This second proof, using the exact same trick of flipping the diagonal, gives us a concrete sea monster that we know lives perpetually in that ocean.
So let's just take a breath and recap this whole journey, because it's a big one.
We started by establishing that infinities come in different sizes, with countability as our yardstick. We saw how robust that smaller infinity is, how you can list all the integers, even all the points, on an infinite 2D grid.
Then we applied that to computing. We proved that the set of all possible solutions, all computer programs, is just another one of these countable sets. We can make a master list. P$, P1, P2, our little island.
Then we unleashed Cantor's diagonalization argument, twice. First, abstractly, to show that the set of all simple problems is uncountable, proving that the ocean of problems is infinitely uncountably bigger than our island of solutions.
And then a second time, more constructively, to build the paradoxical self-application function, self-action, a concrete, uncomputable monster that breaks our list and proves that some questions, like the halting problem, are fundamentally unsolvable.
And the ultimate takeaway for you, listening to this, is that the limits of computation aren't technological. They aren't about needing faster chips or more memory. They are logical, built into the fabric of mathematics itself.
Yeah.
We are logically destined to be surrounded by an ocean of unsolvability.
We have to live with the weight of that truth. The problems we can solve are the rare, listable exceptions. The uncomputable problems are the norm, the default state of the logical universe.
So, since this self-application function is really the gateway to the halting problem, let's leave you with a final provocative thought. This whole paradox, this inability of a system to perfectly predict its own behavior, it's rooted entirely in self-reference and negation. I will do the opposite of what I predict I will do.
Right.
So think about where else in the world, far outside of computer code, we see these kinds of unavoidable paradoxes that stem from complex self-referential systems. When a legal system tries to define the absolute limits of its own authority, when an economic model have to account for the fact that its own predictions will change how investors behave.
Or even when we, with our own consciousness, try to objectively measure and understand that very consciousness.
Exactly. If simple, formal computational self-reference creates these black holes of uncomputability, what does that imply about the ultimate limits of prediction and understanding in human or natural systems that are far, far more complex than any list of programs?